So here's a quick agenda of the session. I'm going to go overview of our architecture. Anyone over here used Solar 1.3 or 1.4, have experience with it? Okay, great. And anyone now running Solar Cloud and running multiple clusters, have experience with that? All right, cool. That's great. So you guys are a perfect audience for it. So I'm going to quickly walk you through our old multi-core architecture, what it is and why we started with it, and then go about some of the pain points we encountered with it and how it kind of made us rethink our deployment and why we went through. And then a quick overview of our hybrid cloud architecture, which is a combination of multi-core and Solar Cloud. And then some of the metrics, benefits, and everything we received moving to Solar Cloud. And then going forward, the evolution of our old architecture into what it has become today, which is search as a service within AOL organization as a whole, where others can use it, and then future work that we are planning to do. And then in the end, we'll take some Q&A so that you guys can get any questions answered that you haven't. So here's a quick 50,000-foot view of AOL Mail. Over here in the middle, you have the mail core component. This is the component that gets information from all the different endpoints. On the top, you have the front-end layers like LMTP, SMTP. That's the deposit flow of the mail. And then you have your IMAP, POP3 clients, and everything. These are all your Thunderbird, Outlook, your mobile phones, and everything. And then you have, of course, your AOL webmail, which uses RESTful APIs and connects via the web. And then on the directory service is where it goes around, looks up the account information. And then we have our own sharding logic that we implemented that routes the information. You have the metadata store where you have all the mutable information, like, hey, which inbox does the mail belong to inbox, who the sender is, quick snapshot information that you would do when you list a message. And then you have the blob storage, which is the bulk storage component where your actual raw message is stored, and then you have your attachment and everything else. And then on the topic we'll be discussing, that's the index store component. That's the third component of our backend infrastructure that I run, and that's where Solar is. So the mail core component over there actually takes the information and creates a Solar document and then sends it out to the index store. So that's at a high level what you want to know. And then over here, so this is the architecture. We are trying to, our mail provides a very complex and a unique problem for us. We have a split mail problem in the sense we have billions of writes coming into our system for millions of users on a daily basis, but not every user is searching. And searches are like maybe a small percentage, a fraction. So we almost have a 15-to-1 search, insert to search problem. And over the years, we have been trying to optimize it, have a single infrastructure, a single architecture, try to accomplish both. And in the end, we figured out we have to break this problem apart and solve it in a different way. So just to give a concept of the scale and the way we are running, this is a number today. We have over 200 physical hosts, physical beefy boxes that are running, and over 3,000 Solar actual JVM instances that run in production for us. A few years ago, with our old multi-core architecture, we used to be having about 1,000 physical hosts and more than 6,000 instances running to spread out the load and satisfy the search use cases for our user. Our index size itself is over 400 terabytes, close to that. It's scaled. Every document of a person that comes into our system, we want it available and searchable for them. So that's the size and scope of our problem. So rebuilds and upgrades, and when we lose things, bad things happen, and it's not an easy problem to solve. The next is number of, as I mentioned, we have over 50 million of users in production, usually using and interacting with our search infrastructure. On an average daily load, we get over 1 billion documents of inserts and deletes happening simultaneously. And as you know, deletes are really expensive in Solar. So that's one of the bottlenecks and issues that we have to overcome. And then we have about 70, 75 million searches, really. And our current availability, with all these problems too, our current availability is over 99.99. So anytime an insert happens or a search happens, we are able to satisfy for the most part without any problem. And another biggest major obstacle we had to overcome over the years is now we have a new mailbox that's created and who only has like a couple of messages. Those mailboxes are really small, a few kilobytes, whereas you have users that have been loyal AOL users for years, and they have probably meg or even a gig size mailbox. And some of our Solar Cloud shards and indexes, they're about 100 gigs scaled out. So a quick overview of our old multi-core architecture. So as I said, we started using Solar with Solar 1.3 timeframe, and at that time, Solar was, even today or to a certain extent, Solar is built to work with one large index with periodic updates and a lot of searches going to it. That's what it's built for. But we kind of did some optimizations and changes. We had Shalin and Noble, who are Lucene committers now and working with Lucidworks. They were AOL employees then, and they had really in-depth knowledge of Solar. So they made a lot of changes to optimize the throughput and make sure like we have things like that's available today, like transient cache and transient cores and everything. Those were some of the concepts you built up. So over here, we have a multi-core farm with over 1,000 physical boxes. On each box, you have an instance of JVM running, and on each instance, you have a dedicated user core. So as you can see, on each instance, you would have about 10, 15, 20,000, and this farm is spread across over thousands of hosts. So this actually started working out. It worked well, but then eventually over the years, as we scaled this up and we were migrating from an old legacy infrastructure to our new Solar infrastructure, we found some issues that kept on coming. One of the things was the dependency or the bottleneck of I/O. A user gets a mail at midnight or today in the afternoon or at random periods of time, and as we index the document at deposit, the user Solar code needs to be loaded into memory, and then that single document has to be put in for that user, and then the user doesn't do a search because it's an incoming mail. He's not doing anything with it. And then periodically, the core has to be flushed down back to disk so that that data is persisted and everything. So that was one of the biggest pain point. The next thing was we couldn't have backups for this in this old architecture. As I mentioned, a user core is transient. It comes into memory, and we have logic where if the user core has not been used for a while or hasn't been done any work, we flush them back to disk. The snap puller model, where it's a pull-based model for Solar replication, that would not work. So we had to decide that, hey, we can't back this up like this, so we disabled replication. So Solar kind of ended up became a single point of failure. At that point, if a host goes down, or if a disk corrupted or anything, that user search is not available. And as you can imagine, when you have 1,000 boxes and 6,000 via instances running, that became more than once on a daily occurrence. And that was something we had a dedicated person constantly going around and fixing. We tried other replication capabilities and other items that we could do. We had another concept called NVR replication that was a product. It was more of a file system rsync sort of thing. We tried doing that. Eventually, since Lucene is based with all these index files and everything, it led to a lot of core corruptions, and we just abandoned that. Since we were I/O bound, we have the optimization point we figured out for this multi-core architecture was we had to eventually do a disk commit only once every 5 minutes. So the moment a user got a mail, we couldn't commit it immediately because the system, especially 1.4, had did not have a document writer per index or something like that. So there were some optimizations that were lacking at that time. So we decided that you can only commit once every 5 minutes. This led to the point where if a user got a deposit or whatever, and then we had an issue with the box and the instance crashed, we could be missing documents for the user. We used to get user complaints like, hey, I know I can see this mail in my list messages, but when I search for it, it's not showing up, or I have to scroll down to message 100 or beyond and then try to get it. So these are some of the things we were fielding. And as I mentioned, there was, due to the variation in the size of the cores, Solar cores, we had a high variation in response time. Usually we would average around 30, 20 milliseconds on an average, but we would see that our large or faithful users who have large indexes and everything, they would see anywhere between over 100 or 150, 200 milliseconds, which was horrible. And then, of course, the biggest pain point that we had was a large number of input, and then frequent hotspots was the biggest problem. So there wasn't any load balancing mechanism or anything, so a user got created. He is assigned to that shard. That mailbox could grow really big, or it could be a normal user who's not heavy user. So since we didn't have an easy way of moving these people around, they would just get stuck, and we would have constant hotspots, and operations and our team has to constantly monitor disk space, move them around and everything, which actually usually ended up sometimes having to rebuild or degrade their search experience. So this is not all lost. Over the years, till like 2011, we did move from 1.4 to 3.5, and then eventually from 3.5 to 4.2. And just running this old multi-core architecture, it's present in our current architecture. We do have the multi-core farm. We did see a lot of benefits just upgrading Solar, and now it's running 4.10. One of the first things when we went from 1.4, 3.5, and I think to 4.2, we saw a huge benefit just in response times. We saw a 75% reduction in response times. Disk utilization went down considerably. I think one of the features that came out was a document writer per thread. We saw 15% reduction in CPU usage, and overall this helped our garbage collection and everything. So we were at a good point when we came into 4.2 and things were going on. So moving forward, we wanted to fix this problem, and we wanted to move into our, coincidentally, as the community was coming up with some of the discussions about solar cloud concept and everything, we were coming in for a hardware refresh, and we wanted to like refresh our hardware, bring in new hardware. So this was like a perfect opportunity for us to think, hey, we have these pain points, we know what's going on, and let's try to figure out a better way to do this so that we are not constantly having a bad experience for our user. So one of the, before you look at the right side, I would like to focus on the left side. If you look at this, this is the same architecture we had. We had the mail core cluster talking to the multi-core farm, and to help with this, what we did was pretty much we had the split bin problem. We had a bunch of inserts coming into small cores and that were going up and down. So one of the first thing we wanted to eliminate was to get rid of that. So we decided, hey, let's go ahead and put Solar Cloud on top of it. All the users can be sharded and moved around, and the load is distributed. So we can just, when we are running queries, we just filter based on the GUID. The documents for a GUID are routed, and the mail core cluster can put the results together and set it. So when we started looking at this architecture and we moved to this architecture, the first thing we saw was all the inserts only need to go to the cloud part, which we decided we'll run it on SSDs because that probably gives us the best performance for our load. So we went ahead, we started working with 4.0 Solar, and there were many of the things that were missing that is available now in 5.3 and 4.10. So we kind of built our own custom doc routing capability and everything, and which it's very similar to the Murmur hash logic we have. So the users document go here. Almost all the deletes also go there because people tend to delete the newest mail they get. That's our user profile. So we went ahead and implemented this. It took a few months, and now this is across the board in our production. The job of the mail core cluster became really simple. It just talked to Zookeeper, figured out which shard to route the document to, and send it to that cluster for that user. And to get a high-level picture of this, so this architecture is like multiplied across 40, 50 times for our scale. So repeated, we have like a user's information lives in almost like an area code, zip code perspective. So all this search information, metadata information, so those guys kind of live in that. So for a particular user, he would have most of his newest documents in the Solar Cloud cluster, and within the multi-core farm, within that itself, within a zip. And then searches were put together. One of the thing we wanted to avoid when we changed our architecture, as I mentioned, is we have a very large index complex. And if we drastically change it, or if we decided just to go from multi-core to cloud, we would be forced to re-index them. And this is something which, cost-wise was not feasible, time-wise was not feasible, because reindexing over 150 billion documents is not an easy task, and nobody wanted to do that. So to go ahead and do that, we just put Solar Cloud on top of it. And another thing we figured out is our indexes are constantly growing. People get mail messages, they keep them, most of them just leave it on their inbox, read it. Nobody tends to delete it, so we do have a problem of a continuously growing index size. So SSD space, which is where the Solar Cloud is running, is not, it comes at a premium. It's not cheap. We didn't want to keep loading that up and generating bloat. And also the use case we see is for our users, people either tend to search, or mobile apps or phones tend to search newly delivered messages like IMAP polling sort of thing. They use search APIs to do it. Or the user usually searches for something he received like a week or two ago or even a few days ago. So that's the use case. So we saw that most of the recent searches can also be satisfied by Solar Cloud. So we said we will leave like 2,000 documents in the Solar Cloud. And for every user, you would have up to 2,000 documents. And anything that goes beyond that, we're going to put it in the multi-core farm. It's almost like a second tier, not really slower in any perspective. It just has to support searches for the most part. So for that, we developed this archiving tool. We call it Cloud Archiving Tool, CAT. What this does is it takes, initially, we had the split and merge logic built into the cloud, which uses the shard splitting and merge logic that Solar at the moment has. We have a similar logic, and we used to just take Solar Cloud and just put it in the multi-core form automatically. What we figured out when we rolled this out into production was split and merge logic is extremely CPU and disk intensive. It's almost like a optimize / compaction and everything, and segment merges and everything. So we decided that's a bad idea. We need to get out. So the archiving tool, what it does, it's a simple high-level logic. This is custom code. Was it takes a snapshot of the Solar Cloud, figures out all the users that are living in that shard, and figures out who are the users who have gone over some configured threshold. So we decided we don't have to do an instantaneous split and merge for users, so we'll passively split and merge them. So we copied off box over here, put it on a different host, and then whichever users we have, we capture their snapshot of their multi-core, put it together, and then the archiving tool figures out, takes a split of the cloud index, merges it with the multi-core index, and then pushes it back to the multi-core farm. And during this operation, this happens at a nightly. We can configure it to run once every night, once in the evening, maintenance hours and everything. So this gave us a lot of benefit. And we continued to save our SSD space. So now we have an ever-growing size of complex at SSD, which is at a premium. We don't overload it and just use it up for messages that are not being searched or quickly queried. This protected us from minimizing the impact for our live production users. We don't have any of those problems previously. Some of the benefits we came up with our hybrid cloud architecture, the first thing is cost savings. Now, you may wonder, hey, this seems like more beefier machines. You're using SSDs. How did you go about cost saving? The first thing is we got hardware that actually on the same host, we have SSD and SATA drives, which is a combination you can get anywhere. These are really beefy machines. They have like 24 core CPUs, 150 or 160 gigs of RAM, about 1 terabyte of SSD and 2 terabyte of SATA drive space on the same physical host. So previously, we had 1,000 hosts distributed, spread across, be like one of the largest footprints within AOL for Solar. We shrank that considerably into about 200 physical hosts by just moving our architecture. And that itself saved us a lot of money in the sense of we don't have to buy more racks, network connection cables, and everything. And that saved a bunch of money. Next, moving to SSDs, previously I mentioned how we had variation in response times, where we used to get anywhere from 20, 50 milliseconds for the multi-core. When we moved to SSDs and started doing it, our average update time, it's writing to a live core that's always in memory. The document is getting routed and immediately inserted. So we saw like 10 milliseconds on an average. And then searches did not degrade as much as we thought it would, because now instead of doing a search on a small core, which is only a few megabytes, you're trying to do a search for a user for a phrase on a core that is like a few gigs, 130, 40, 50, or 100 gigs. We did not see a lot of degradation. We actually saw like a slight improvement of 5 milliseconds on an average on our search response time. Previously, as I mentioned, we used to commit a document for every 5 minutes. So a user who just previously got it, or the mobile application that tries to search it, the document will not be available for 5 minutes. People do have a tendency to send a message or in their phone, and then they try to search it on their sent folder to see if that message was sent or properly. So that was one of the use cases we saw. And for 5 minutes, we would not be able to show that. So people did have a bad experience. Now, using SSD, we are actually doing hard commits every second. So this has changed our user experience considerably. It's like instantly there we've got feedback like, wow, this works great when we rolled out this architecture. And most importantly, using cloud and using 2 shards and having a failover of a shard protects us, and Solar is not a single point of failure over there. And if you remember in the architecture diagram I showed you, there was the cat tool, and then right bottom there was a cold storage. So previously, we couldn't have a replica for our multi-core farm because there was a in-memory, come in, get a document, and disappear sort of model. So the slave pool model would not work. But with our cat tool, what we figured out was the multi-core copy, for the most part, remains static. It only supports searches and deletes. We can temporarily fail deletes while we are doing the split and merge process. We copy it, and then we just throw it on a different slower tier hardware. So if ever we lose the multi-core farm for whatever reason, disk failure or whatever, our searches can go to our cold storage. And reindexing became very painless, because when you had to reindex a user's information, you caught information from the cold storage, put it in there, and you had partial search for the documents for that user in the Solar cloud. So all you had to reindex was a missing small delta between cloud and multi-core from the previous snapshot. So this was hugely beneficial, and we are in the process of rolling that out. And then this is some of the metrics that I wanted to show you in the terms of response time when we moved from our old architecture, multi-core architecture, to our hybrid cloud architecture. Inserts came down considerably, deletes and searches. And deletes are very expensive in Solar. We'll get to what are the pain points now that we have some of our Solar cloud, hybrid cloud architecture. The first pain point we started seeing was the disk space issues. So we noticed over time, as we were running this over a year's time, was Solar would create these index.timestamp files as replication between 2 shards. If there was a network issue or the inserts were constantly happening, they would get created. And we've seen some of them just lingering around and not getting cleaned up. I think in 5.3 or something, there was a Jira for it that seems to clean up stale index.timestamp directories or whatever. So we are excited to look at that and see if that fixes one of the problems. Right now, we have a script that goes around and cleans them up if an index.timestamp directory hasn't been touched for a while. This was something we figured out in production. It was a pain point. The other thing we noticed was we have the merge scheduler, and merges run. We have it configured with concurrent merge scheduler and tiered merge policy for our Solar cloud. But we do notice that occasionally 1 or 2 shards, don't know the reason why, they continue to not clean up their deleted documents. This has happened multiple times live in production. And what happens is, well, let's say we have 100 gig of SSD space, a logical volume separated for a shard. If it's at 30, 40, or even 50 gigs, and we force and optimize, it cleans up, everything is good, it's great. But occasionally, if you're not monitoring it, and we figured out this hard way when we were running in production, if we do not take quick action on a particular shard, it would go up to 70, 80, and pretty much fill up the disk 100%. And you would look at the index, and it would say, hey, I have 40 million documents, but your live documents or active documents are only 10 or 15 million, and the rest of them are all marked deleted documents that haven't been compacted, and the segment merges haven't done. So right now, as we haven't completely solved the problem or force optimize, we are thinking of running a force optimize, but the version of Solar we are running is 4.10. So when you do a force optimize or optimize script, it'll go around and run across the entire cluster. So we want to see with 5.3, you have an ability to say distribute equals false and just optimize one shard or a one node. We are saying if that'll help us out. One thing to mitigate this problem, what we have done is leave 60% of our SSD space available, so we periodically monitor it, and we've gotten really good at monitoring and alerting when a disk space goes about 40-45% of the allocated disk space, and then we try to clean up immediately or increase the threshold or decrease the threshold in CAT to remove more documents from the cloud and send it to the multi-core. That's something that does pose us a hard business case to put to our management when I have to say, hey, you have to leave 60% of SSD space free and empty. It's a battle. Another thing we have seen in Solar Cloud is the Solar Overseer node. This is with 4.10. I know there have been some changes and upgrades made it to 5.3. The Solar Overseer node either is overwhelmed or goes through a GC pause or whatever happens, it eventually stops processing the Overseer objects in the queue, either the thread dies or whatever. And eventually what happens is the Overseer in the Zookeeper or Overseer queue continues to fill up. And if you know this or not, every time a node goes down or comes up, there are multiple stages it goes through. It goes to down, gone, recovering, and then active. And when it's in recovering mode or down mode, requests are coming to it. It constantly bombards Zookeeper by filling up the queue, saying, I'm still in recovery mode. If it doesn't do for every request, it does for a set of requests. So that was one of the things we figured out the hard way. So now we have a script that goes around and cleans up Overseer queue and also alarms when we look into the Zookeeper and say, hey, the Overseer queue is filling up. The other thing we saw was in 4.10, the Cloud Solar J had a 10-second timeout talking to Zookeeper. So this impacts the mail core system, is when it would come up, if it had any network issue or something talking to Zookeeper, it would wait for 10 seconds for every request for every user. So that was something we would see a cascading effect of stuff bottling up on our front-end client and then impacting our users. This would actually manifest in the way of actual deposits for mail slowing down, and this would just back up the queue. So we put a change in 4.10 to make that configurable to 1 second or less than a second to come on. The other major problem we have over here is our search infrastructure, as you could see in that architecture diagram, is very tightly coupled with Solar. You have this the multi-core or the Angelia core thing, which would, the mail core, sorry. The mail core would have to talk to Solar Cloud, especially for a search case, figure out, get a set of documents, and then talk to multi-core from, get a set of documents. And if it's time sorted, it's really great because we know for the most part, Solar Cloud has most of the newest documents. But if it's sorted by subject or sender or any other sort field, it has to get these two resulting document lists, put them together, sort it in memory, and then try to send it to the end user. So we figured out, we have to start thinking about in a broader perspective and say, we have to decouple this and make search as a service. We have a really scaled, really well-maintained architecture that we have gotten a good handle that scales up very well, that's provided a lot of cost savings, and it has 2 tiers of search capabilities, so 2 tiers which helps you with different use cases that you want. So we wanted to explore the opportunity of how do we go about leveraging this and making this better. So one of the things you see over here is this is our old Solar architecture, hybrid cloud architecture that is still there, and the mail core doesn't talk to it anymore directly. So what we built was a system in the middle, which we call as Search FE, and it's just a pass-through system. It's a RESTful, fully supported RESTful API system, runs on a Tomcat. It runs pretty much on VMs. It's not a really intense application. And what it does is it decouples the mail core system with this. And it also provides us an ability to expand our search offering to other services if we need. And also, if we decide we want to move away from this architecture, or we have a new set of users that we want to throw in public cloud. I'm not saying we do right now, but like we want to put them in AWS, we want to put them anywhere else, or we want to try Elasticsearch cluster or whatever. We want to do that if that gives us complete flexibility and it makes up a seamless layer to expand and evolve our architecture. The search FE farm, previously you saw there was a directory lookup service that would go around and figure out where a user's document lived and everything. We just moved that, ported that information to a sharding configuration and shard mapping into a MySQL database external to it. So this architecture gave us a lot more flexibility. But one of the things we noticed, I'll get to that in a minute, was this also came with a set of problems of its own. So we are looking at fixing that, and we have a couple of ideas. But just to give a quick example of what the API looks like, we have something generic API, host port add document. You give it an ID, which would be like your user ID. Type of application, whatever. It's like, hey, it's mail. It could be service 1, service 2, photo service, whatever, if you decide to use Tika and do that. And then you specify a format of response you want, and then you actually give your document. Simple update JSON document that you want in text. You would probably get a response in the following format of a response code, status detail, and everything. And in the detail section, if you were doing an actual search, you would have your search results, documents, and everything. It makes the integration of new components and new systems very easy, and we can just this also provides other developers in our team not to worry about search. They don't have to know schema changes, what version of Solar, what's the JVM configuration, how do we deploy, is it cloud and everything. They just come and talk to us, ask us, hey, this is a problem we are trying to solve, this is the load, help us with it, and we'll just take care of it. And they don't have to change any of their clients to talk to us. So one of the issues that we saw going into the search FE architecture when we went into mail is a dispersion of a problem. If there's a bad user or a bad document or something, previously a user's information would go to a specific shard. We could quickly identify it and everything. With the new architecture, that became a little bit spread out. So we have to track that user. So we had to go through multiple logs of FEs to figure out what the response was and stuff like that. And then another thing was a slow node on let's say we have a slow shard or a slow node. That would impact at a broader scale, because the FE VMs they have, like, let's say 100 threads, and they're talking to 3,000 different nodes. And if one node is slow, that node is going to start taking 10, 20, 50 connections across your entire complex, and you have 99.999% of your complex running happy, healthy, but the FE becomes your bottleneck because all its threads are being used up. And we saw this happen more than once in production. So to come up with these issues, we figured out some of the quick solutions we could do. One of the things was we started putting in tracing a user request across multiple systems. So now if there's a problematic user, we can just, we have another system that is for maintaining our logs, so we can quickly find exception issues and everything, trace it down. The other thing is this is something that I've worked in the last few weeks. We incorporated a library called Hystrix. We also have our own internal library that we could also use. So we wanted to, this is at a high level, Hystrix provides a flow control mechanism. When a request comes into a particular dependency, it allows you to check for that dependency, monitor that particular dependency, and say, hey, if this one is failing X number of requests, fast fail, or don't allow more than 5 threads concurrent requests for this particular endpoint. So incorporating this into HTTP Solar Server provides us the capability that if a single node is timing out frequently or is constantly erroring out or it has out-of-memory issues or whatever, we pretty much have an ability to fast fail and mitigate that. So we prevented the cascading effect where a slow node with take down resources on the FE, which would again end up taking resources on our services in the layer above, because everyone is waiting, so we can just move faster. Some of the future work that we are planning to do is we have solar across cross data center deployment. So we actually have 5% of our complex right now having this, where we have 2 data centers. We have a shard 1, replica 1 is in data center 1, and then shard 1, replica 2 is in the data center 2. And we've actually seen it to work without any problem. There isn't a major latency issue across data centers that have cost us a lot of trouble or anything. So that's something we are really excited about, and in the near future, we want to push it out to 100% of our complex if possible. The next thing we want to start looking at is to upgrade to Solar 5.3. We are running Solar 4.10.3, which is like maybe 6 months or 5 months old, and we want to get some of the new modifications and optimizations, especially with the Zookeeper and Overseer stuff that the community has worked on. And also, we want to remove some of our old customizations and stuff we've done since 1.4 because our architecture has changed. We had stuff like F-Sync disable and special exceptions and everything that probably don't do it. The next thing we want to start doing is fault tolerance tuning for different systems. As you can see, our architecture has changed. We are not just going to probably be doing it for mail. We are going to do it for their different subsystems. So we want to start tuning timeouts and hystrix configurations for different of them. And then we also want to something we don't do right now is look inside attachments. We do see that a lot of our users have PDF attachments or images and everything, and it would be a great feature or function if we can like make that searchable so that they don't have to rely on the subject or a sender to look for a particular maze, and this also improves our relevancy from our user perspective when they're searching for something. I think I'm out of time, so any question, Q&A, and that's my LinkedIn information, and you can shoot me an email. Any questions? Yes? Pardon me?
How do you set a single account from the cloud?
You mean in the cloud world? So you wanted to move from one cloud to another cloud? Is that the question, or? Yeah. So from cloud to multi-core. Yeah. What we did was, I don't know if you have an experience with the shard splitting logic within Solar Cloud that is available. We use something very similar, but it's a little bit customized, where we have an index reader for an index, figure out the documents for that user, and then we use a merge index writer or whatever, and then merge it into the multi-core. And at a high level, actually, if you let me go back really quick to the architecture picture. All of this is actually Solar running in different modes. This is actual Solar binary. This is actual Solar binary. And this is actually the same Solar binary, just running in different modes, talking to different endpoints. So like the archiving tool has ability to all the Lucene and Solar APIs that are regular once you open up Solar that you have. So we didn't have to like really figure out how to parse a Lucene index or do everything. It's actually identical schema. You just take a small sliver of documents for a user and then merge it into the multi-core. And it's the same schema. It just goes in and merges together using the merge segments API and everything. Yeah. Any other questions? Yes?
Do you have a use case where you want to send across all mailboxes?
We haven't had it, but we would. We can actually do that because the Cloud Solar JI supports multi-cluster, multi-cluster search capability, multi-collection, sorry. And the search FE farm, we could tune that if you ever had a use case like that to send it to multiple Cloud Solar Js, or even if you don't want to use Cloud Solar J, these are all HTTP APIs, so we can just search across the board. It would be a simple tweak. Load balancer for Cloud Solar J, you mean for the users that are created within where they are created within the cloud so that their documents get routed to? Yeah, so the shard configuration and shard mapping layer kind of figures out, we tweak the numbers within it. So we say, hey, send 10% of user creates to this cluster, 20% to this cluster based on the disk space availability and the load and everything. So that's how we go about load balancing them. And usually once a user is allocated to a zip code, he kind of like lives there and everything. But with this model, we have other tools actually that we monitor disk space, load and everything, and we can just move them around. Mm-hmm. Yeah. So every user, since he belongs to that, the search FE farm is behind a whip. So it just comes into the whip, hits any farm or any VM in the search FE farm, and it has the ability to just go look up in the config database which zookeeper it needs to talk to and just routes it to the correct user based on that. Yeah, so every user is associated with like an endpoint in this configuration, in this mapping layer, and then we say, hey, for this application, for this user, you live in this cluster, just go route the request over there. Yes, but that's one of the layer we are adding Hystrix support for, so that if for that one user or set of users a particular node is bad, you can continue routing it to everyone else. Just ignore those guys for now till we have a maintenance issue. Yes. We don't store almost any part of the mail document in Solr. I would not recommend at this moment with the Solr to store anything. It bloats our index unnecessarily. We have also seen Solr when there's like a mismatch, when the two shards go down or two replicas for a shard go down simultaneously for some fat finger or some issue. When it comes back, they can't figure out who the leader is, and they kind of like delete the data and start from scratch. I've seen that happen a few times. So we don't really permanently store anything on that. And I would say we would store actually very like few components. We don't store anything major of the mail. Everything that is there is for specifically for index and searching only. Yeah. That's a temporary outage we are taking. So one of the things we are doing is going across data centers for that. So that situation never happens. We want to mitigate that and go about that. Originally, we did put them in like different racks or in the same rack, but we have had issues where like an availability zone disappears and all the shards are gone. So we are trying to do it. One thing we do have is our Zookeeper ensemble is in 3 different data centers. So usually that's pretty reliable, but we have seen issues. So that's one of the reasons why we're going across data centers. Yep. Any other questions? All right. All right. Thank you. Thank you very much. Yep.